Pyzdek Institute.
So what we see here is an interesting quote. There are three kinds of lies: lies, damn lies, and statistics. And that's a quote from Mark Twain. At least it's attributed to Mark Twain. He attributed it to Disraeli, but most scholars agree that Disraeli didn't say it. So let's just give credit to Mark. I'm going to talk to you about the statistical lies. And I also want to give you another quote from Mr. Twain that I'm going to go into in the end. And it's been the way in which the issue of statistical lying has been addressed. And primarily it is, when in doubt, tell the truth. So if you can't avoid lying, quote unquote, if you can't avoid distorting the statistics, at least let the readers know that you've done it, and point out some of the ways in which you were not able to control the data. First of all, what's a surprise? Well, it's a legitimate statistical result that contradicts our expectations. An absurdity, on the other hand, is an unexpected result that leads us to a conclusion that's not true. So, for example, you may have data on a call center that shows that people who've been on hold for an hour are just as satisfied with the service that they received as people who were only on hold for 1 minute or less. That's an absurd result. And what probably is happening, if you give it some additional thought, is that people who don't mind staying on hold are staying, and people who are upset are actually leaving. So sometimes the statistical results are absurd, and if you're in the business of Six Sigma, Lean Six Sigma, you don't want to be called on ideas, trying to defend ideas that really are indefensible. Lying with statistics, well, that's a special kind of lying, because that's using statistics and numbers to give a misleading impression, and often this is done deliberately. Sometimes it's done accidentally, and it's important to understand how this happens and learn what is, in fact, misleading so that you can avoid it when you do your presentations. So a statement that uses statistics to convey a misleading result is the worst kind of lie, according to Mark Twain, and I tend to agree with him. One kind of lying, or one kind of problem, is sample bias. So, for example, well, first of all, let's talk about a sample. A random sample is a sample in which every observation or every person or thing in the population has an equal chance of being represented in your sample. Let's consider a statistical claim for a university. Then they say the average salary of our graduates is $100,000 a year. Right away, your antenna should go up. Your thought process should begin to ask questions such as these: whose address or phone number is the school likely to have? Is it more likely to have alumni club members or graduates who are homeless, people who don't even have a phone? So if the answer is one or the other, well, then that group is going to be more heavily represented in the sample. Well, considering, let's say they do have all of the data that they need, they do have all the names, and they can contact all of their alum, who's most likely to respond? Successful alumni or unsuccessful alumni? Again, there's another source of bias. And let's consider that we're asking people how much money they make. Which is more likely? Respondents who will overstate their income or respondents who will understate their income? And to the extent that these questions and many, many others lead to a sample where the people in it are less likely or more likely than those in the general population to be in the sample, you have a sample bias situation. Accurate responses don't affect the bias. So if we're looking at people overstating, people understating, and people telling you their correct income, a person who's telling you the correct number is not biased, and so therefore their response will not affect the bias. And at this point, I want you to just think in your own mind other sources of sample bias, and I'm sure you can come up with several. And when you look at any statistic, be it a statistic like this one or even a statistic that you get from your Lean Six Sigma projects or quality improvement projects, consider the possibility that it may be biased and try to measure that bias so that you are dealing with accurate data. Another way to mislead is just to use a summary statistic. And really all statistics are summaries. You're taking a large number of values and you're reporting a small number of statistics to represent these values. So let's look at averages. What might be wrong with an average? Well, let's say we've got some salary data. We have salaries from our previous report of 50,000, 50,000, 70,000, and 500,000. Based on this data, would you say the average salary is A, $50,000, B, $167,500, or C, $60,000? Well, the correct answer is all of the above. A is the mode. That's the value which occurs most often. That's $50,000. B is the arithmetic mean. So if you sum those numbers and then divide by the count, you'll have an answer of 167,500. It's very heavily influenced by that extreme value of $500,000. And C is the median. So if you have an even number of values, the median is midway between the two middle values, midway between 50 and 70, you get $60,000. So the question would be, I guess, which of these most accurately represents what you're trying to convey to the audience for your data. It's also possible that your sample will have some data represented more heavily than other data. So for example, here's some data that shows a U-shaped pattern. Off to the left we see a peak, flattens out. Off to the right we see a peak. It's possible that because of underrepresentation in the smaller group on the left and overrepresentation of other values in the large group on the right, you can get a pattern that's distorted, so it doesn't look like the original data just because you've got more of one particular data value than another. And this actually occurred. So in one of the IPCC reports on climate change, there was a chart published that statisticians analyzed, and the original chart showed what was called a hockey stick pattern with a flat line for about 1,000 years followed by a sharp upward spike. And that was because there was an overrepresentation of a particular type of data. When the data were corrected and the statistical errors taken out, you had more of a U-shaped pattern. So even scientists that have millions of dollars in their budget can make these mistakes. Another way to misrepresent the data or lie with statistics is selective reporting. So if you watch commercials, oftentimes the company will represent their product with the statistic. They're going to tell you something about their product. It's the most popular, it's the most reliable, etc. Well, here's one way in which they may give you a result that needs to be questioned. Let's say that you have an ad and it says 8 out of 10 dentists prefer your toothpaste. Well, one way they may get that ad is by taking a number of small samples and then picking the one that gives the result that most favors their product. So here's the sample that they picked, and indeed 8 out of 10 dentists in this sample preferred Smiley toothpaste. They failed to report, however, that in another sample only 2 out of 10 dentists preferred their toothpaste. And what they're doing also with this is they're taking a number of small samples and cherry picking. So they're picking the result that favors the position that they want to convey. I'm actually old enough to remember ads like this. Back in the day, they ran ads just like this one. In fact, this is a real ad. More doctors smoke Camel than any other cigarette. Well, what don't they tell you? There's missing information. First of all, most doctors don't smoke. Even back then, these were called coffin nails and cancer sticks for a reason, and most doctors understood that there was a health risk if it hadn't been measured and quantified like it has now, but they understood the risk and they knew it was there, and most doctors didn't smoke at all. They didn't offer that choice, and had they offered that choice, probably the ad would have said more doctors don't smoke than smoke any other cigarette. Another thing is they would often advertise things like Chesterfields have less tar than any other brand. Well, if you take a metric, a measurement, and you rank order the results, something is going to be the smallest and something's going to be the largest. So there's a statistic that can be reported. It sounds very powerful and scientific, but in fact, it has no meaning at all. I've actually seen charts like this when presented in meetings, and this is a chart where you can pretty much say whatever you want to because there's no scale. On the left-hand side, the actual results of the scale are missing. You'll see a lot of these in newspapers where they're making a point about a trend, but without that value, you can't really evaluate the trend. So you have to have a scale, and the scale has to be correct, and correct depends on just how just what you're trying to tell the audience. So the correctness of a graph depends on the message you're trying to convey. So for example, here's a chart where you have a strong upward trend, an apparent strong upward trend, and you say summary headline on the chart, prices skyrocket. But if you look at the scale, this time we got the numbers on there, you can see that between the first quarter and the fourth quarter, prices only increased by 0.15%. So this is not as large a price increase as the chart makes it appear. And what we can also do is we can make this even more dramatic by changing the chart scale. And on this chart, you see the same value of 0.15%, only it looks even bigger. And the reason it does is that instead of starting at 0%, like the previous chart did, we're going to start with the smallest value of 0.1%, and we're going to truncate this chart at the highest value. So now we made 0.15% look even larger. And this is a way to distort the impression that you get from the chart by distorting the scale. That's why a chart like a Pareto diagram has a very carefully defined axis. The Pareto diagram is going to start at 0 on the left and right axis, and it's going to go to 100% on the right axis and to the close to the total, cumulative total on the left. That's because we want, when we're doing a Pareto analysis, we want to compare the bars to the total problem. We want to see how much of a contribution they're making to the entire problem that we're trying to study. Modern computers will let you create charts that use images, so you can assign an image to the bar and the chart will rescale the image according to the values on the chart. So you have to be careful when you're using a picture to represent some metric, and I'll show you why. Let's say that we have a picture of an item or an object such as a cow, a house, a car, and normally in the real world our minds are conditioned to look at these things in 3 dimensions because that's what they are in the actual real world. One common mistake is to pick an aspect of that image and use it to represent our metric. So let's say we're trying to show what happens when the price doubles from $2 a pound for beef to $4 a pound, and we decide, well, sounds very reasonable. We're going to put an image that's 2 inches tall in there for the $2 a pound cow, and we're going to expand that image to 4 inches when we're representing the $4 a pound cow. So let's see what happens. So here's a cow. We're representing $2 by a cow picture that's 2 inches high. When we increase the height from 2 inches to 4 inches, what we see is that the image of the cow expands by more than that. So if our mind looks at this, we see that the surface area has doubled, and in fact the total volume of the cow has increased by even more than that. So again, that's something we may innocently do and inadvertently give a misleading impression. A couple other kind of statistics I want to talk about. One of them I call is a say what statistic. And a say what statistic is missing something. It's generally a statistic that's missing the denominator. It's missing the base, missing what we're using as a standard for comparison. So for example, I might say lean organizations are 20% more efficient. If I don't say what they're more efficient than, I've got a say what statistic. And what you need to do when you hear statistics is try to contemplate what the statistic is actually saying. And if it doesn't make sense to you, stop the person who said it and ask for clarification. If you don't do that, it's just simply too easy to get the wrong impression or the wrong idea. And often the speaker won't even know they've done it, and it's going to help them convey a clear message to everybody. Another kind of statistic would be a so what statistic. And these are numbers that are provided by people who don't have any special qualification. So for example, if I were to tell you that more black belts preferred Puff's facial tissues, the correct response from you would be, who cares? Black belts are no more qualified than anyone else to make this assessment. And you'll often see celebrities testifying before the House or in front of the Senate committee on things such as topics of interest to them. And while we all recognize the celebrity and his opinion or her opinion may be an interesting thing to know about, you still have to bear in mind that they really probably don't understand the subject matter any more than you do, and therefore they're no better qualified to make a judgment than you are. Quite often we're looking at data in tables, and it's very important to analyze the data correctly. So here's data. The data is made up, but the problem is not. This was actually a lawsuit, and it involved gender bias in school admissions. And what you can see from this table is that we have a school that had a certain number of males apply for admission, and the acceptance rate for the male students was 70%. We had a similar number of females apply for admission, and their acceptance rate was only 40%. And it certainly appears that this shows an indication of gender bias. The males are being accepted into the university at a much higher rate than the women are. But it happens that this particular school had another variable that needed to be considered. They had two programs. The top table represents a program with a very tough admissions criteria, so a lot more people were rejected at that school than the bottom college. And the bottom college easy admission data shown in the table on the bottom. So here what we have is the males, 200 of these applied for admission. Into the tough program, the admission rate was only 20%, so only 40 out of the 200 were accepted. 800 women applied, and out of the 800, 200 were accepted, so their admission rate was 25%. So what you see is that more women were admitted to the tough program than men. So now we no longer see the bias and may even see a bias in favor of women applicants. On the bottom chart, we see that 800 males applied for admission into the easy to get into school, and 83% were accepted. 200 women applied, and all of them were accepted. So again, the women had a higher acceptance rate than the men. And if you add these numbers together, you'll see that again we have the same numbers that add up in the total for the original table. So we have 660 males plus 40 males, that's 700 who were accepted. We have 200 females in the tough program and 200 in the easy program, so that's 400 women. And the numbers in this original table are just split up according to some classification category to create the numbers in the two smaller tables. This actually has a name. This is called Simpson's paradox. And it occurs anytime you have a table with data in it that can be classified according to another variable that's not shown in the table. And you see it can actually reverse the direction of the relationship. So you have to be quite careful when you're looking at data in tabular form to be sure that you're actually not masking a relationship by excluding another variable. Here are some statements that are true, but they're misleading. Let's assume the following. For every 100,000 people who don't drink our soda, yippee, 99,999 will survive for a year. But our yippee drinkers have a slightly lower life expectancy. So out of 100,000 yippee soda drinkers, only 99,998 will survive for a year. Well, it's quite possible that the yippee drinkers enjoy yippee so much that they're willing to take that slight additional risk. But let's consider how this would be reported in the press. This is a true statement. Drinking yippee doubles your risk of dying. Well, how can that be? It certainly doesn't appear that it's a big difference between the two. It happens when you report the relative risk instead of the absolute risk. The risk for non-yippee drinkers is 1 in 100,000, while the risk for yippee drinkers is 2 in 100,000, and the relative risk is this larger number divided by the smaller one, and that's your relative risk, and that's 2, and thus the headline. It's not inaccurate, it's absolutely correct, but it's quite misleading. Let me give you an example from today's news. So this is a headline from the London Daily Mail. Taking painkillers long-term triples the risk of kidney cancer. I mean, how scary is that if you're taking aspirin or ibuprofen for your arthritis or some condition that you have? If you read this article, it's quite a long article, at the very bottom you're going to find this. The overall risk of renal cancer is small. Only 6 per 100,000 people are expected to develop this. So that means that out of 100,000 people, 99,994 people will not get renal cancer. And if you break that up between those with painkillers who are taking painkillers and those who are not, the small additional absolute risk is very tiny. And it's quite possible that a person who needs painkillers because they're in pain would accept this small additional risk, but that headline is likely to scare them and cause them to make the wrong decision. Well, there actually now is a field that's been spawned about 20 years ago, and it's a field that looks at not just medical science, but all research. It's research, you know, is an industry. It's worth several $100 billion a year, and it deserves our attention. And this particular school of thought has looked at medical research, and I want to show you some other examples of medical research that have been discovered and are hopefully in the process of being corrected, but they still have a ways to go. Here's a typical example of a reputable journal reporting a result. In this result, they looked at the scientific study and the summarizer study in their article, and their conclusion was painkiller taken by millions can increase the heart attack and stroke risk by 40%. Now that we know that they're talking about relative risk, we know that we can't really evaluate this number unless we see the raw data. And the raw data for this particular report is not made available in the article. And in fact, this report is a summary of other research. So it's not actual research, but it summarizes actual research. And that involves a number of other risks that we're going to talk about in a minute. So here we go, 40% increase. What does it mean in terms of us making a decision? We can't say because we don't have the data to assess this properly. This study came from a peer-reviewed journal, which sounds impressive until you look at that journal and you see that it also published a paper called Why Most Published Research Findings Are False. So basically there are a lot of different reasons, but the truth is we have to be very careful when we use the findings from reported medical research to make decisions about our lives and the health of ourselves and our loved ones. But what they have started doing as a result of all the work that's been done, some journals anyway, have required the authors to point out the limitations of the study that they're familiar with. So this is the study that was reported on the previous page about the painkillers and the risk of heart attacks. First of all, it relied on observational studies rather than randomized controlled trials. So this is the weakest kind of medical research, is an observational study where you're actually just following a large group of people over a long period of time, and these people that are included are really not controlled for in any meaningful way. The data in the studies came from large administrative database and may not have been comprehensive. So we have missing variables. They don't include information such as non-prescription drug use, aspirin, and so on and so forth. And we already know from the Simpsons paradox analysis that could make a lot of difference. There were confounders. So some of the people may have had heart problems and other things going in that caused the data to be skewed or biased. Suffered from heterogeneity, so they had a number of different studies collected on different groups of people at different points in time for different lengths of time and so on. And so they're mixing apples and oranges, and that throws doubt on the findings of these systematic reviews. To give you a case in point, cholesterol studies often include a group that's known as hypercholesterolemic. And these are people who have a genetic predisposition to be extremely sensitive to their cholesterol intake in their diet. And if those groups are included in the research groups, you'll see a much more pronounced effect of cholesterol on heart problems than if that group is excluded from the data. So the final word, don't let this happen to you. Be very careful. Try to do your best to tell the truth with your data, control for bias, and take large samples. Try to randomize your sampling process. And just as the morals of the story, as I see it, are twofold. One is a thing is more than the numbers that represent it. You can't reduce any real-world thing, especially a person, but also a process or a product or a service. You can't reduce it to a set of numbers without giving something up. And the second thing is, if you have a large set of numbers and you summarize those numbers with statistics, you're going to lose something by creating that summary, and you have to understand there's no way to avoid it. You can only be aware of it.